Okay, so let's look at the key exchange lab. So in this lab we'll be looking at some basic principles around the Diffie-Hellman method, also elliptic curve, and a little bit on trust infrastructures. So the first thing that we're going to do is we're going to look at the basics of Diffie-Hellman. So if you remember, we share a G value between Bob and Alice, and we also share a prime number. So what we do is that Bob will take a value of b, little b, and then create the g to the power of little b mod of the prime number, send that's big B, send that to Alice. Alice will take her random value, a, little a, and take g to the power of a, mod the prime number, send that to Bob, and then each of them will raise it to the secret value that they have, and they should end up with the same shared key. Okay, so we'll give this one a try here. So you can use a calculator, but I'm going to just use Python here to help me out. So G is 2, 8, 7, 9. And N is 9929. Okay, Bob selects a value of 6 and Alice 9. Okay, so we'll now calculate G to the power of X mod N. And then we'll calculate Bob's value. Alice's value. Okay, so now they're going to exchange it. So we'll take Alice's value to calculate the key, and we'll take the A value that we get, raise it to the power of Y, and we'll take the B value that we get and we'll raise that to the power of X mod N. Okay, and the reason this works is that they will end up with a value of g to the power of xy mod n, and it works because we're using the mod of a prime number. We can still use all our maths like multiply, divide, add, subtract, and to the power of through the magic of this mod of a prime number. So let's see what we get. Okay, and there we go. Okay, so we've ended up with the same number. So it shouldn't be possible for Eve to determine the value of x and y, and thus to find out what the shared key is. Obviously we're using very small prime numbers, and it will become more secure if we use a larger prime number, such as for 768 or 1024 bits. That's a very large number. Okay, so if you try that out, create Bob and Alice. If you have, if you're doing it with someone in the lab, then share values with them and see if you end up with the same shared key. If not, if you're doing it remotely, then just create two examples and pass parameters in between. So we can use OpenSSL to be able to create these parameters. So remember we saw G and N. So they're the core of Diffie-Hellman method. And if we're using Diffie-Hellman method for IPsec, VPNs, for SSL and so on, then we need to generate a G value and an N value. So we need to watch that we don't use the standard default values because they could be pre-computed. Okay, so let's quit from here and we'll open up our SSL, and I've just pre-prepared it in here. top of that. Okay, so this is going to generate our Diffie-Hellman parameters for us with a 780-bit prime number. And the generated value is 2, and we are using a 768-bit key. Okay, so hopefully it should be a safe prime number. Our generated value is 2. So we'll just list the file that we've created. There we go there. So there's our prime number. So if you count, you should be able to get that that's 768 bits. And we're using a generated value of 2. Okay, and all contained within here, if we need to pass this to our device or the other side, then that defines the parameters of the prime number and also of the G value. And if I now try, this may be too slow, so if you timed that, probably took about a couple of seconds, so it might take a little bit longer. So we now go up to, that was group 1 that we created, now we'll try group 2. Group 1 shouldn't really be used in a secure environment, but we'll try group 2 now, which is 1024-bit prime numbers. So, it's not too bad there, but we'll just list our parameters again. And we should be able to see that the prime number is longer this time, and the generated value is still 2. Try group 5 and see how you get on. We change if we don't like the 2 value for our G, we can create an option of -5. This time we can see that we have a generated value of 5, and it should create a prime number which will work with 5, and then we'll just let's have a look and see what our parameters are, and there we are there, a generated value of 5. So we can either have 2 or 5. If you look in the manual for OpenSSL, and let's see if we can find where it is in the manual. So you should be able to find from there the -5 value. It's a bit difficult to find from there. So have a search in the manual and see if you can find the -2 and the -5 option. Okay, so that's Diffie-Hellman. So Diffie-Hellman's not used that much now because of security issues, but it's still often there in terms of setting up VPN and so on. And certainly you should be using group 2 at least, and hopefully you could use group 5. Remember that once you've created your keys, then it's a fairly fast process. So the main hit that you take is in generating the keys. So generate them as strong as you actually need them. So we can also use OpenSSL to do our elliptic curve, and okay, so we can list the different elliptic curves that we have with this command here. So they're not, it's not like RSA where you've got 1024 bits. They're much smaller. So there's brain pool, and there's other ones here. You can see these have only got 163 bits and so on. A typical one that we would use is the 160-bit one. That's 160-bit prime numbers. So we're going to end up with smaller values for our keys, and this is the one that's used in bitcoins and in blockchain. That's a 256-bit prime number, and it has the strength well over 1000 bits RSA. Okay, so now what we'll do is we'll generate some keys. Generate a key pair using the 256-bit version of Elliptic Curve. Okay, so this is really just to generate the parameters that we're actually using and not the key pair yet. So if we now take this for our parameters, we can show what those parameters are. So there's the prime number that we're going to be using for our operations. We have an a value and a b value. So our curve becomes y squared is equal to x cubed plus 7. Because of this, there's no x value in this curve. And for elliptic curve, we have an x, y point. The 0, 4 doesn't count there for our x, y point. So there's an x, y point in there, which defines the generator point on the curve. Okay, so that's our parameters. So finally, let's generate our key pair. Okay, there we go. So just generate that. Okay, so our output is my key.pem, and there we go. So that's showing us our private key. So from there we would be able to put that onto our server and to be able to decrypt or check the signature of anything, or to decrypt anything that was actually sent. So for the next part, what we'll do is we'll try out a few examples here. So if you want, you can write your own little Python program here. But I'll just paste this in. Okay, so when we have a g value of when we have an x value of 3, we get 8. An x value of 4, we get 5, and so on. And what you should find is that it will be cyclic. We will get a unique value for all the values up to 10. And then when we get to 11, it goes back to the start again. Okay, so it's cyclic in nature. So if we try for 12, it goes to 4. Okay, so it should go 2, 4, something, something, something. And then each one giving a unique output for all the x values. If it doesn't, then the g value doesn't work for that prime number, and we must pick another one. Okay, so that's what happens after we go to 10, goes round again. So let's try a g value of 3. And now let's start with 1. 2, and now 3, 4. Okay, so we see we're coming back round again here to value of 4 and a value of 1. So a G value of 3 isn't working because it's not given as a unique output for the values of x and there. So we couldn't use that G value for that prime number. Luckily, we've got a little Python program that we can actually run to be able to determine if it's a good value, a good G value for a certain prime number. So we'll just have a look at this program here. Okay, that's a prime number of 11. So we just run this and see what we get. Okay, so for a prime number of 11, we can use 2, 6, 7, and 8 as a G value. We can't use 3. Okay, so that shows you the values that we can use for our G or our generator for this, for the discrete log, for a certain prime number. Okay, so you can try 41. So if we have a prime number of 41, so obviously when we're calculating our Diffie-Hellman parameters, the program would check, the generator would check that the G value was acceptable for that value. So we'll try 41, and that'll be safe. Okay, so for 41 we can use 6, 7, 11, 12, 13 and so on. We probably want to pick as small a value as possible because we don't want too large values being created. Okay, and then we have a little small program here. Which will basically do the key exchange for us. So we can see that this is the value that Alice sends, this is the value that Bob sends. They swap over, and then Alice takes Bob's value and raises it to the power of A here. And Bob will take Alice's value and raise it to the power of B, and then get the same. And then what we've done is that we need to now generate a certain size of a key. So let's say we were using 256-bit AES. We now put it into a hash function. So we'll take the key that we generate, and we agree on both ends that we're going to be using SHA-256, and it will generate a 256-bit key for us. So let's give that a try, and hopefully that'll work. Okay, so you can see here, if we try a few times, there's the keys that we're getting, 191, and there's 1, and so on, 4, 5, 6, 8, 2, 8, and each time when we generate the key we'll get the same one. Obviously in real life we'll be using much larger prime numbers. Okay, so try it with some different G values and P prime numbers, and see if you can get one that doesn't actually work from there. And then we've got a man in the middle type attack here for this one. So this is where Eve sits in the middle and negotiates a key between herself and Bob, and herself and Alice. And as far as Bob and Alice know, then they are communicating with each other, but there's actually 2 keys involved. So let me see if I have that. So that's for C. Okay, so let me just copy and paste this in there. just to see if this is going to work. Okay, a lot of printing going on there. But if you follow through the example that we get here, so Eve is generating her own random number, 7 in this case, and she will take either value and raise it to the power of her value, and then send that back, and she'll end up with two keys. One she uses with Bob, and the other one she uses with Alice. Yep, it's not pasted very well. Random base 64 for key generation #lib, which should be installed. And if you're using any arguments, then you'll be able to add that in. Okay, so we can see here that Alice and Eve are using one key, and Eve and Bob are using another key. Alice will sit in between and then decrypt in between that. And so now we'll look at some elliptic curve. So with elliptic curve, we take a point on the elliptic curve, and then Alice generates a random value, which is a gradient, and then we'll publish our public key. It's an XY point. Bob does the same and takes a random value, multiplies the generator, which is both shared by Bob and Alice, and then creates a B gradient, and then creates a public key point. From there, they pass their public key values. Alice multiplies the value she receives by A, her random value, and then Bob multiplies his value by B, and they should all end up with B times A times B times G, the point, mod P. So they will end up with the same value. So it's not like the discrete logarithm problem. It's an elliptic curve problem where we now multiply the points. So let's see how we get on here. Let's see if I've got the code right. Good. So I just run the code first, and then I'll explain how it's all set up. Okay, so in the end we end up with the same session key here. Okay, the session key will relate to the size of the key that we actually want to generate. Okay, so if we look at it, so initially we're creating, let's see where we are. Okay, so we're creating a random number here, and we're creating our A value, and then we're creating another random number there, and creating our B value. So let me see where we are. That's not the right code, just let me check. Okay, so let me just paste this from here. in a little bit strange, so let me update it. So in this example, we only using 32-bit random numbers. Obviously, you wouldn't use that in real life because these are too small. Okay, so Alice creates a 32-bit random number, then takes the point on the elliptic curve. The elliptic curve is 25519, and then take the G value that's well known in that curve, and then multiplies A to find her public key, which is a pub. Bob will do the same, get a 32-bit random number. That's too small, remember. In normal cases, multiplies that G point on the elliptic curve and then finds the public key. They then pass each other the values, and then Alice will take Bob's public key value and multiply it by A. Obviously, all this is done with the mod of the prime number. Bob will take Alice's value and they'll multiply by B, and then hopefully KAB and KBA are equal to the same thing. Okay, so we'll just install ECC snacks. Okay, so that's installed. So we just use a pip install, and then hopefully now when we run our program, we'll be in there. Okay, so we can see here what we've got. There's Bob's public key point and Alice's public key point, and in the end they're sharing the same value. Okay, so that's the way that that elliptic curve Diffie-Hellman actually works. So obviously we wouldn't use such small random numbers. So let's actually try with bigger ones. Such as for 128-bit. Okay, so often we use 256 bits for our public key encryption with Bitcoin, but we use smaller ones there. So I'll give that a try. And unfortunately, we've went larger than this package will support. So we'll just drop down that to 64 bits. Give that a try. Okay, so it's not allowing us to do it. So you can drop it back down to 32 bits, and it should be possible for you. Okay, and then with this one, we're creating what's called a key distribution center. So we'll try this one. Okay, in this case, Alice and Bob generate the long-term key. When Bob wants to speak to Alice, then he will get back. They will generate keys based on both their long-term keys. We can expand this so that we get back Alice's encrypted key. So the KDC can actually create a session key, and then it can be encrypted back to Bob and Alice, who can then decrypt with their key. Or what can happen is that the KDC sends back to Bob an encrypted version of the session key that only she can then decrypt, so he passes that through. Okay, so have a look at this code and see how you get on. With this last one, we Bob and Alice agree on the value of 5 with a prime number of 97, and then we can see the values coming through, and what we'll do is use brute force to be able to determine what the values of the random values that have actually been used. So I've mocked up a very simple program here, and it just goes round till it finds a value that matches. So we have a G value of 5, an A value of 32, 41, 97. Okay, so as we saw before, if we use the correct G value for the prime number, it should give us a different output up to p minus 1. So we should only get one value which will match the value that Alice sends, and the same for Bob. Okay, once we've found the A and B value, we can then calculate the secret key. So we'll give that a try. And the value is 74. So G to the power of 74 mod 97 should give us our value of 32, and then 5 to the power of 85 mod 97 should give us 41. We take the A and the B value, 74 and 85, take G to the power of A times B mod P, and it gives us 72. If we now try to use a value of G, which is not possible, which will not give us a unique output up to p minus 1, such as 2. Let's see what happens. And you see here we're getting 2 values for A, and we don't get any values of B. So it just doesn't work. Okay, so make sure that the G value that you create will allow you to be able to create only a unique output of A and B up to p minus 1. Then you can create your own little program here that will solve for these things.